Okay, so in the first few sections of 2.1, we were talking a lot about linear equations, how to solve linear equation graphs, different forms of linear equation. In 2.3, we're going to look at linear inequalities. All right, so we're going to understand what a linear inequality is, kind of go over interval notation and set notation, because those are the solution sets to linear inequalities, solve them symbolically, which remember means algebraically, and graphically, numerically go hand in hand. And then we'll get to compound inequalities. All right, so first, what's an inequality? So an equation involves an equal sign, right? In order to be an equation, you have to have one side equal to the other side. Well, an inequality is you replace the equal sign with an inequality, which is either a greater than, a less than, a greater than, equal to, which that's what the little bar underneath means, greater than or equal to, or less than or equal to. And so some examples are, I've got x plus 15 less than 9x minus 1. The next example is I've got that quadratic, x squared minus 2x plus 1 greater than or equal to 2x, and so on. And so linear inequalities have usually infinite sets, meaning the solution to them, right, either there's no solution, or typically there's infinitely many. There's a group of numbers that will make the inequality true. All right, we're going to look at specifically linear inequalities in this section, so how to solve them, how to write their solution sets, and so on. All right, so linear equality is whenever I have an equality where I can write it in the form I have one variable part, right, which we're writing as x here. I can combine all my terms to get down to one x term, one variable term part, and one constant. All right, and I can always set it equal or greater than not equal to. I can put my inequality on the side of 0. Right, so it'd be greater than equals 0, less than equals 0, and so on. All right, so the following example are all examples of linear inequalities. The first one's the case where it's in the form ax plus b is greater than, or actually in that case, less than 0. But the rest of them are also inequalities. I just have to do a little bit of manipulation to get them there. And we'll talk about how we manipulate these expressions. It's the same stuff that we did with equality, except for one extra thing that you have to know about inequalities. But all of these, if I manipulate them algebraically, I can put them in this form. One x term, one constant term, and I can set it to 0. Either, again, one of these forms. I can set it greater than 0, greater than or equal to 0, less than 0, less than or equal to 0, and so on. Alright, so my example here, before we get into the properties of inequalities, is this is again an example where I've got 7x plus 5 greater than x. And I can put it into one of these forms. All right, what I have to do is I have to subtract x from the side. Right? If I subtract x from both sides, that zeroes out on that side, so I get the 0 here. I take 7x minus x, that's where the 6 is, and the 5 is just 5. I didn't need to add or subtract anything to it. All right, so I can put it in the form. And so the rules are basically you have the same rules for inequalities as we did for linear equations, except you have one more sort of rule you have to watch out for. And it is that one more rule that will catch students off guard. All right, so the first one would be the same thing that we did with equations. All right, if I have an inequality, so if I have some expression A less than some expression B, I can add or subtract the same number to both sides, as long as it's the same number. So if I've got 6x minus 3 less than or equal to 10, I can add 3 to both sides if I wanted to. Right, so 6x less than or equal to 10 plus 3 is 13. Right. 2 is I can multiply or divide. Now the catch is here if it's a positive number. Right, it's equivalent if it's a positive number. So I can add or subtract to both sides, or I can multiply and divide, right? Because multiplication and division are the same. Division is just multiply by the reciprocal. And so using this example above, my 6x less than or equal to 13, if I want to get rid of the 6 on the x, well, I divide by it. Right? 6 is a positive number, so I'm okay. So then I get x less than or equal to 13. Alright, and the same thing would work if I multiplied as well. Right? As long as it's a positive number, I'm fine. Where the catch is in the additional pieces, if it's a negative number, I multiply or divide by. If it's a negative number, you have to flip the inequality. So if it was a less than, you have to flip it to a greater than, or vice versa. If it was a greater than, you have to flip it to a less than. And so an example would be, suppose I have negative x is greater than 10. Just a simple example. And so I divide by my negative 1. This rule means I have to flip it. X then is less than negative 10, right? X is less than negative 10 because I have to flip the sign. Now remember, my original equation was negative x was greater than 10. You can always check your answer. Pick a value that you can check. All right, so pick a number less than negative 10, so I'll let x be negative 20. So if I plug negative 20, and that's true, right? Negative 20 is less than negative 10. And if I plug negative 20 in here, I get negative 20, right? Negative 20. Is that greater than 10? And it is, because the negatives cancel each other out, leave me with 20 is greater than 10. And so you can always check to make sure your answers are true. Right? And when in doubt, the biggest thing, and again, this is the thing that most students will forget, if it's a positive number, I don't have to worry about it. Positive numbers are fine. If it's a negative number, you have to flip the sign. You have to reverse the inequality. If you don't reverse the inequality, you'll get the exact opposite answer that you really want. All right, and again, you can always check your answers to make sure by plugging something in. All right, before we get into, so I have one more thing before I stop this video and start into solving, which will be the next video, is just reminding you of set notation and interval notation, right? We like interval notation, but you should also know how to kind of convert between the two. Right, so an example would be, suppose I have the set every x such that x is less than or equal to 10. Remember, if it's the equal to case, we include the endpoint with a bracket. And so the interval notation here would be, well, it's less than, which means I'm shooting off to negative infinity, 10, but I've got the equal to, that's what that bar underneath means, so equal to 10. And so if I'm including 10, I put a bracket there. The difference between that and, say, greater than 10, well, greater than 10, there's no equal to. Greater than means I'm shooting off to infinity, so I start at 10, but this time I don't include 10. If I don't include 10, it's a parenthesis. A parenthesis say I'm starting at 10. It's my starting point. It's everything after 10 works. And it's forever, so infinity. You always put parentheses around infinity because you can't ever reach infinity, right? It's never equal to infinite. Same thing's true if you have a between, so every x value such that x is between 3 and 10, right? Meaning my x value is equal to 3 and bigger than 3, but less than 10 and not equal to 10, and so I'm between 3 and 10. I include 3, I start there because it equal to, but I don't include 10. All right, so again, the biggest thing is if the endpoint's equal to, bracket. If the endpoint is not equal to, parentheses. Right, and then we're going to get into solving and writing them in both those notations. So again, this is set notation. This is interval notation. All right, so set notation, interval notation, you should be able to understand what both those mean. Right, and we'll get that. So we're going to pick up answering or solving systems of inequalities in the next video.